Our speaker today is Marius Oancea from Max Planck Institute for Gravitational Physics in Germany. Marius is visiting Professor Korzyński, and he's a PhD student of Professor Lars Andersson. And today he will tell us about his recent research about gravitational spin-Hall effect of light.
Yeah, thank you very much, and thank you, Mikolas, for organizing this and inviting me here. It's a pleasure to be here. So I'm going to talk about my main research project, which we call the gravitational spin-Hall effect of light. And if you come from condensed matter physics, this should ring a bell, and I will try to emphasize the direct connection of this gravitational effect with the ordinary spin-Hall and Hall effects that show up in condensed matter physics. Okay, so let me start with a short motivation. So how do we treat the propagation of light in general? So in general relativity, we have null geodesics, and in quantum mechanics, we have photons that follow ray trajectories. However, in all this standard text...
What about Maxwell equations? Propagation of light by Maxwell equations.
Yeah, exactly. So the null geodesics come as the zeroth order geometric optics approximation to Maxwell's equation. Yeah, so they are underlying Maxwell's equation.
But there are also exact solutions with Maxwell equations on the gravitational background.
Exact solutions in what?
Exact solutions.
I'm not sure.
Of Maxwell equations, for example, in this partial method.
Yeah.
So you
yeah, but I'm thinking about localized wave packets.
So what? Maxwell equations describe all wave packets.
Yes, I agree with this.
So I don't understand then why Maxwell equations are not being used to analyze.
No, they are being used. They are being used. I'm not excluding Maxwell's equation from this picture. I'm just saying, when we think about light in, let's say, high school or in first years when we study physics, we are taught in general relativity that light follows null geodesics, or in quantum mechanics we talk about photons that follow ray trajectories, which basically are the same null geodesics.
Photons do not follow ray trajectories. Photons have wave functions, and wave functions of photons in quantum mechanics obey Maxwell equations.
Yes, I agree.
I think the second point is a little bit misleading.
Yeah, we can ignore the second point. We can ignore the second point.
Half integrals.
No.
Propagates everywhere, and that's.
I'm thinking about classical Maxwell's equation and all the content that.
I can agree that the light can be described within the general relativity theory in a full generality.
So I'm going to emphasize at different points along the talk that we do not need quantum mechanics to describe any of these effects, and all these effects would follow up from classical Maxwell's equation. Okay, but what I want to emphasize here, for example, when we think about null geodesics, the spin degree of freedom is generally ignored. And the main question is this always justified? So, for example, if you look... Of light, yeah.
This is called polarization.
Yes. Yes. So this is generally ignored.
Using spin is misleading because spin is part of angular momentum.
Yes.
And spin separately does not make sense because there are no states that have definite spin. They can only have definite angular momentum.
Yes. Okay, so if we look at condensed matter physics, for example, during the past 20 or 30 years, let's say, there has been tremendous progress because people started considering the spin degree of freedom of the electron, for example, and looked at the consequence of this. Okay? And the second part of the motivation comes from an analogy between electromagnetic waves propagating in curved spacetime and electromagnetic waves propagating inside some inhomogeneous optical media. So, for example, we have the equations that describe electromagnetic waves in curved spacetime are formally equivalent to the set of equation describing the propagation of electromagnetic waves inside some optical material in flat spacetime. And on the other hand, restricting to some material in flat spacetime, starting from Maxwell's equation inside such a material, one can derive some spin-dependent propagation of light, or polarization-dependent propagation of light, and this has been confirmed experimentally by several groups using different methods. So, using this analogy between the equations in curved spacetime and equations inside some inhomogeneous media, it is natural to ask the question if one should see a similar effect in curved spacetime. And this is what I'll refer to as the gravitational spin Hall effect of light. Sorry?
With the refraction index, which is space-dependent.
Exactly.
But also time-dependent?
Yes, it could be also time dependent. I mean, it's a bit hard to define the refractive index when you have a time dependence of, let's say something like a Robertson-Walker
It's much
metric.
more complicated because
Yeah.
there's a tensor.
Yeah,
in the
exactly.
space and they're off diagonal elements.
Okay, so I'm going to start my talk with an introduction to the Hall effects in condensed matter physics, and then slowly go towards the spin Hall effect in inhomogeneous media by introducing the angular momentum of light and the different spin-orbit interactions of light. And then I'll present to you three different approaches towards the gravitational spin Hall effect of light. The first one is based on methods adapted from relativistic quantum mechanics. And the other ones are a bit more traditional in the sense of general relativity. The first one being the Mathison-Papapetrou-Dixon equations, and the last one being the standard geometric optics approach to Maxwell's equation in curved spacetime. And then I'll end with some conclusions and a list of open questions. Okay, so let's start with the ordinary Hall effect. I assume many of you are familiar with this, but let's review it. So if we have like a piece of metal and we have a current flowing through this piece of metal, we have the electrons going from right to left here. And now let's say we apply an external magnetic field in the z direction like that. So what will happen, we'll get a Lorentz force acting on the electrons and the trajectories will get bent. And the charge starts to accumulate on the two lateral sides of the conductor. Due to this charge accumulation, we will get this transverse electric field, which will tend to compensate the Lorentz force of the magnetic field, and then we will, in the end, we will reach a steady state regime. So this is the ordinary Hall effect, and it can be measured as a potential difference on the lateral sides of the conductor. Okay, we also have the anomalous Hall effect, in which case the effect of the external magnetic field is replaced by an internal property of the material, namely the magnetization of our sample. Okay, but how about this, if we look at the spin degree of freedom instead of the charge degree of freedom? So in this case, we can get what is called the spin Hall effect for electrons in condensed matter physics, and this has been predicted in 1971. So basically, if we have some special material which has what are called spin orbit couplings, then electrons will get scattered, will get some spin-dependent scattering. So let's say in this case, spin-up electrons will go one way and spin-down electrons will go the other way. And then in the end, we'll get some...
Is this the magnetized sample? Or there is an external magnetic?
No, it's an internal property of the sample.
What the electrons scatter?
So let's say we have some impurities, for example. We have some impurities of very heavy atoms. These have large spin orbit couplings, and then you get some spin-dependent scattering onto these impurities.
Depends on what happens to the spins of those scatterers. Are they arranged in a special fashion, or these spins of those scatterers are also randomly distributed?
I guess they could be arranged.
This is a paramagnet. So the scatterers are in a paramagnetic phase. They are not.
Yeah, I'm not entirely sure, because I think there are two or three different scattering mechanisms.
Because if you have a sample with the magnetic impurities, and they have and suppose there are no electrons, then the question is
need to be domains, otherwise you wouldn't see the separation.
If you have a magnetic materials where there are where the
I understand this will not play a significant
No, it's
role. Not in this talk.
it's
In physics, of course.
yeah.
I'm terribly sorry, but it plays dramatically role because the domain drops
Not
are.
in this talk.
There is accumulation of a spin and there is no usually.
So it's just for the analogy. I don't want to go into the details. I mean, it's a completely different subject of looking at the spin Hall effect for electrons. So far we just say that we have some sample that has some special properties that scatters electrons in this particular way.
Spin dependence.
Yeah, exactly. Spin dependent.
Dependence.
Yeah, and there are several underlying mechanisms in condensed matter physics that will give this this sort of effect, and it doesn't help us in going into the details of it for the purpose of this talk here. Okay, so far this has been for electrons. So the next question that we should ask is what about light? What about what happens when you consider the propagation of light inside some inhomogeneous medium, for example? But before going to this, it is helpful to review the types of angular momentum that light can carry. To be more specific, I'm going to focus here on paraxial beams. So considering paraxial beams of light, there are three different types of angular momentum that light can carry. So the first one is I assume it's well known, is spin angular momentum of light. It's related to the polarization degree of freedom that comes from Maxwell's equation. And for example, if we take such a beam and we look per photon, the amount of angular momentum carried per photon in such a beam is quantized in units of h bar. We can have plus or minus h bar, and this would correspond to circular polarization, to right-handed and left-handed circular polarization of light. Okay. The second type of angular momentum is called intrinsic orbital angular momentum, and this is not so well known as.
It is well known. These are metal beams.
Yes, I agree. No, I'm saying that usually I give this talk to the GR community, and they basically know nothing about this. So in that sense, I say that this is not so well known as the spin degree of freedom.
It's out of independent statement, of course.
This is absolutely wrong because helicity cannot be multiplied by L. I mean, this is helicity, P over P, right? This is called helicity.
Yeah.
For particles. And how come you multiply this by L orbital momentum? This doesn't make sense. What kind of classification? I understand that you want to classify the states of the photon using L quantum number, right?
No, I'm just saying that in this case, if you have the beam, and if you look in that beam, if you look how much angular momentum per photon does it carry, then you get this this answer.
When you have a beam, a Bessel beam, it has total angular momentum, which cannot be separated into the spin part and orbital, because there are no solutions of Maxwell equations that would have one single L on them. There is always a combination, because Maxwell equations describe a vector field, and vector field cannot live with only one orbital momentum. You must have both.
Yeah, I agree that you have both.
So
I think it's going to be a very interesting discussion between you two after the seminar. I just want to raise the issue because Professor Bianicki sorted it out, and I think is the world's best specialist and has a numerous string of physical review letters pointing out to errors in the analysis of other people. So if this is not very crucial to what you are going to say, further on about propagation of light in gravitational field, let's don't argue about it. I strongly encourage the two gentlemen talk.
Yes, I agree.
We have a huge blackboard in the corridor,
I agree.
which you can use.
Yeah.
And
I get all the feedback. I mean,
on the Project Nature Photonics article, so I guess it would be best to contact the authors.
Yeah, I definitely recommend this paper. It's really.
for the purpose of this seminar, it's important that those two gentlemen come to some sort of internal agreement.
Thousands wrong papers.
Yeah, okay.
Okay.
Let's go.
Okay,
The
so
most interesting part is propagation, of course, through the
Yeah.
gravitational field, right?
okay, so let's look a bit how these types of beams are then generated. So, for example, if we start with a Gaussian beam, so this one over here would carry only spin angular momentum, but no intrinsic orbital angular momentum. And say we pass this beam to this material that has this spherical profile. So then it will gain a phase shift dependent on the thickness of this material. And then on the other end, it will come up with a phase profile that has this spiral profile, and then we will get one of these beams with intrinsic orbital angular momentum L equals 1. This is one way to generate these types of beams. Okay.
Does that mean that if this kind of quote-unquote lens would be floating in vacuum, then the beam would propagate through it, and the lens would rotate in the opposite direction?
You mean this? This?
Momentum? Yes.
You mean this material? No, that doesn't need to rotate.
Of course, it will rotate, but
If not suspended, of course.
I mean, if it's not suspended,
You mean?
conserve angular momentum.
Yes. Okay, I see. So that's something different. Yes, I agree.
So there is a force restriction.
Yeah.
Well, in the 19th century optics, it was called the
Okay, so it looks like people doing experiments are very good at generating beams with a lot of intrinsic orbital angular momentum. And here are some examples from people from Vienna who have generated beams with L up to 10 to the power 4 h bar per photon. So the main point here is that if we consider these types of beam, we can put a lot of angular momentum in our beam. Okay, and then there is the third type of angular momentum called extrinsic orbital angular momentum. This is completely analogous to the mechanical type of angular momentum. It's just R cross P. Okay, and now the important thing is that we have the total angular momentum, and then all spin orbit interactions of light come as some interplay between different types of orbital angular momentum. So, for example, if we consider a system where we have spin and extrinsic orbital angular momentum, due to conservation of total angular momentum, we will get spin Hall effects. If we have spin angular momentum and intrinsic orbital angular momentum, we get what is called spin to orbital angular momentum conversion. And if we have intrinsic and extrinsic orbital angular momentum, we get what are called orbital Hall effects, which are completely similar to spin Hall effects. And now we can look at the equations of motion for the spin Hall effect. If we just ignore the red part from these equations, we get just the ordinary geometric optics equations of motion, where our light beams propagate inside some material with a varying refractive index. And then if we take this other correction, we see it's proportional to the helicity and goes like 1 over omega. So, and this will give us the spin Hall effect of light. The point is that this effect goes away in the limit of high frequencies.
This analysis is misleading because photon is not a point particle. You treat photon here as a point particle. It does not make sense. All these mechanical analogies.
So this is an approximation. I'm not saying this is.
But approximation must be valid. So photon is the first particle that wave effects dominate. So treating it as a point particle is not a good approximation.
Well, in some laboratory condition, it turns out it's a good approximation. I'm just saying that in some situation, it's a good approximation. I'm not saying it's generally.
Photon is a point particle?
In some approximation, I think it could be treated in this way.
Actually, detection could be localized and often is, but not propagation.
Yes, so, yeah, I agree.
Approximation would mean that there is some expansion in a small parameter.
Yes.
What is the small parameter in this case?
So one can obtain this equation if we start from Maxwell and do geometric optics, and then
Some H comes into it if you study Maxwell equations. There's no H in Maxwell equations.
Okay. So this is exactly it's a good point. So for example, Brioch treats this as a quantum mechanical effect and says that this comes as a first order correction in H bar.
It's wrong because there
I agree.
is no
I agree.
H in Maxwell equations.
I agree. And this is why I said at the beginning that even though some authors tend to introduce this H bar and call this effect a quantum effect, you can totally get this effect from classical Maxwell's equation without considering any quantum mechanics. Okay, but the main point is here, as I mentioned before, this comes as an interaction between extrinsic and spin angular momentum. So the conservation of the total angular momentum implies these equations.
Angular momentum of what? What is the dynamical system that you want to describe? When you talk about integral of motion, you must have a Hamiltonian, and the generator must commute with the Hamiltonian. Otherwise, it is a notion which has no really definition that you can use here.
So in this limit, we are, even though you don't like, we are treating.
Where do these equations come from in physics?
The nature photonic.
No, but for arbitrary photon field, if you take relativistic angular momentum tensor, its components will be appropriate components which correspond to projections on
Total angular momentum. Yes.
total will be conserved. And now the question is whether you can, from the conservation of total angular momentum, whether you can derive those equations.
No, because in free space only the total angular momentum is conserved. If you have a medium, it is not conserved, then.
Because there is this device which keeps this lens not moving.
Okay, can we can we go on?
That would saturate the angular momentum.
Okay, so these are the predictions. They have been predicted by different authors using different methods, including methods that do not mention quantum mechanics at all, just start from Maxwell's equation and derive this equation using geometric optics. Okay, but the important thing is that this type of effect has been observed in the laboratory in different situations. So here in the first example, you see it as this separation of the circularly polarized beams.
So I have a kind of a transparent tube of
Yes.
material through which I'm sending a light beam,
Yes.
somehow manufactured.
Yeah,
somehow,
exactly.
Right? And what does mean that there is accumulation of angular momentum, you call it spin on the...
No, that was for electrons, so there is no accumulation. I mean, don't think of accumulation here.
No, well, but then what means spin? I mean, there was...
Spin means
was a
spin.
There was an example of a spin.
Let him answer.
Means spin-dependent trajectories. So, as we see here for this cylinder, let's say spin up and spin +1 and spin -1 get different trajectories. So this is what I refer to as spin Hall effect, not necessarily accumulation of spin. So the accumulation of spin was a consequence of the spin-dependent trajectories.
It's polarization,
But
like not spin.
there is no problem with the boundary condition for this classic tube or whatever
It's
tube.
experiment. You just put a beam of light at
Yeah, but this
which
this
is a
beam.
superposition of two
No,
polarizations,
no,
and at the end you
Yeah,
get
but
two
I'm
of
not
them.
talking about the light. There is this
No, but
classic
this
tube.
is about the light.
Yeah, I know, but before I send the light, I have this tube,
Yes.
and this tube is suspended in the air, or vacuum, or water,
okay.
or in milk. So there is a boundary condition, and this boundary condition affects what happens to the light on the boundary.
Of course.
And therefore,
Fiber. This is an optical fiber.
so this, yeah, but then there are special conditions for propagating the light within the optical fibers. And I'm not sure that the
But this is an
solution is...
experimental result. Here, experimental results that propagation depends on the polarization.
Yes, exactly. So
Different polarizations, right-handed and left-handed, give this color.
So that is irrelevant.
Yeah, that is
okay. So this was like the introductory part from optics and condensed matter physics, and now I would like to present 3 different approaches that are present in the literature for the gravitational spin Hall effect. So the first one, I call it the quantum mechanical approach because I agree. Don't. No, I agree. I totally agree. I agree. Because this is how the people that presented this call it, and they use methods from relativistic quantum mechanics. I totally agree that there's nothing quantum about this effect. So I'm just presenting what other people did in the past.
So it's based on the analogy between Eichhorn approximation and WKB approximation.
No, I'm going to explain what they use here. Just a second. Okay, so here they use techniques usually used in relativistic quantum mechanics for the Dirac equation, namely the Foldy-Walthuizen transformation. And then they adapt this Foldy-Walthuizen transformation to work for massless spin-1 fields using the Bargmann-Wigner equation. This is horribly complicated, and I don't want to go into the detail, but we can reach the equations of motion by using this analogy that I mentioned in the beginning, considering space-time as a medium. Then we have the first 2 formulas which give us a correspondence between the metric tensor and the properties of our.
Nice to quote the first author who did this.
I can't remember. I have them written down.
Okay.
I can't remember them.
Because he was a Polish physicist.
Plebanski?
Plebanski.
I think there was someone before Plebanski. But Plebanski is the one that put them in this nice form.
In this formulas.
Yeah. Yeah.
Before that it was a Russian.
Yes, in the 1920s, I can't remember exactly. I have them written down, and we can look afterwards. Okay, but in this way, for example, if we consider Schwarzschild, then we have a clear way of defining the refractive index, and we can basically use the formula that the formulas for the spin Hall that I showed you in the previous slides. Okay, so if we look in Schwarzschild, then we have these very similar equations of motion as the previous ones. Only now the role of the refractive index is played by the space-time. So if we arrange the metric the metric in isotropic coordinates, then we can define the refractive index like this in a very simple way.
This is now the Eichhorn approximation.
No, so the authors.
How come you have a particle?
So the authors over here use this very complicated machinery of the Foldy-Walthuizen transformation adapted to the spin one.
Foldy-Walthuizen is very misleading because it distorts the wave. Distorts the wave function. You should not use it to.
No, I'm not. I'm just presenting it. I'm just presenting what other people have done.
Presenting this.
He's a PhD student and doesn't know everything yet.
Foldy-Walthuizen transformation is
He
a
will know.
non-local transformation. Therefore, it cannot be used to interpret the wave function or whatever wave is coming. It is unitary, but not preserving the local properties. So the use of Foldy-Walthuizen is just wrong in this context.
It is going to be a very productive stay, I think.
The main point is to present the results and then discuss the results. That's the main point. I mean,
The equations are nice.
yeah. Okay, so now we have these equations in Schwarzschild. The first limitation is that their method only works in Schwarzschild, and it would be terribly complicated to extend it to non-static metrics like curve, for example. Okay, so one thing we can do now, since we have this equation, is we can integrate them and get some intuition on how this spin Hall effect looks in Schwarzschild. Okay, so let's consider a Schwarzschild black hole, and then somewhere over here, we consider 3 beams. The blue and the red ones are h bar plus minus 1, and the green one is just the ordinary null geodesic. So for the green one, we see that we get ordinary light bending, but then if we consider the spin Hall effect equations, then we see that on top of light bending, we get this additional transverse shift over here. And we can look at it from another angle. Maybe it's a bit more clear over here. So again, the null geodesic, and then we get this, let's say, transverse shift that defines the spin Hall effect, basically.
Light comes from the top, right?
Yes, yes.
How is this related to the equations for spinning particles that were, for example, proposed by Papapetru and Matison before?
That's the next section after this.
It will be mentioned.
Yes, of course.
And does it have the formula something to do with gravitational lensing computation, or?
Gravitational lensing in what sense?
Well,
So gravitational,
well, okay, bending light.
Bending of light is gravitational lensing, but for example, people that look with the telescope at gravitational lensing, they look at the far field regime, and at the far field regime, the spin Hall effect gets suppressed. So in that regime, they don't really see anything like this.
So you have to be close to the
Yes, exactly, exactly.
It's grossly over-exaggerated here for the illustration.
Yes, exactly, exactly. Okay. And now we can look at some deflection angles and see what would be the magnitude in some particular scenario. So the first line is just the ordinary light bending formula. And then if we look at the light bending due to the spin Hall effect, first of all, it is important. So you see here, ordinary light bending, it's in this plane. But the spin Hall effect light bending, it's in another plane. So it is important that this light bending effect here, it's in another plane. And you see that it has a lambda over R0 factor compared to the ordinary light bending. Lambda is the wavelength of the photon, and R0 is the distance of closest approach to this.
This is the icon approximation, propagation of light in the background metric, is it?
So the first one, ordinary light bending.
This approach. To calculate deflection angle, you could start with the Maxwell equation, but this is too complicated, I understand. So you make an approximation.
Yes.
That the wavelength is short
Yes.
as compared to the distance that is traveled by this beam.
Yes.
That means that this is the icon geometrical optics approximation, light propagation.
Yes.
Yes,
So
it's all about
yeah,
that.
yeah, exactly. Okay. So now we can take this formula for the spin Hall deflection angle, and we can plug in some, let's say, some realistic numbers, or as realistic as possible. So we consider light bending around the sun. We take the distance of closest approach, roughly the radius of the sun. And okay, on this axis we have deflection angle, and here we have frequency. And here the green line represents, let's say, the resolution of the best telescope we currently have, which is the Event Horizon Telescope. Even though the Event Horizon Telescope works somewhere only in this frequency range over here. And then we can plot what we get from the spin Hall equations of motion, with sigma being the helicity and L being the topological charge for intrinsic orbital angular momentum. If we have no intrinsic orbital angular momentum, then we have only h bar here.
You don't have h bar. There's no h bar here. How can you introduce h bar into this?
They like to multiply it by h bar.
What is the reason
They
to multiply
introduce
h
H
bar?
bar by hand.
Yeah.
This comes,
Classical physics.
I agree, but as I told, this is based on the approach by the authors I mentioned previously, and they're considering this as quantum correction, and as h bar correction. So this is their prediction. I'm just presenting their prediction.
How does this prediction depend on h bar? Where does h bar come in?
It cancels out in all these equations, but they just
Okay, so if you look at the deflection angle, I'm sorry, it's my mistake. So exactly, so it's my mistake. If you look at the deflection angle, the h bar cancels out in the deflection angle. So here it would be h bar, it would be 1 instead of h bar.
Cannot be 1. Because sigma contributes 1 and orbital.
So if I take a circularly polarized beam,
Yeah.
then this is what I get, the blue line. This is the deflection angle for a circularly polarized beam. Now,
But there are no beams with total angular momentum equal to 0.
no, it's a circularly polarized beam. It's not 0. And then if
I think the curves are obvious.
and then if I take a beam that has
Forget about the equation.
if I take a beam that has this like a Bessel beam or a Laguerre-Gauss beam that has this intrinsic orbital angular momentum, then the point is that the effect gets amplified with the value of the topological charge. So if I have topological charge 10 to the power 4, then the effect, the spin Hall effect, gets amplified by 4 orders of magnitude. And the point is that, so for the frequency in which the event horizon telescope works, we see that without the intrinsic orbital angular momentum, this is like 4 or 5 orders of magnitude below what it can resolve. But the point is that we can amplify this by using intrinsic orbital angular momentum. And we can get somehow close to the resolution of the event horizon telescope. Of course, the details of such an experiment.
What conceivably can manufacture these kinds of light beams?
It is very easy. You call aliens, another system, tell them to propagate, to make such a beam and send it towards.
Yeah, I already prayed for it.
Powerful mirror and space probe on the Lagrangian point.
Okay. Okay, so I'm just trying to emphasize that the effect is not crazy small. It's not 20 or 30 orders of magnitude away. So if we properly design some satellite probes, or if we properly generate some beams with intrinsic orbital angular momentum, then the effect might be observable. It's not totally impossible. That's the whole point over here. Okay. Some other consequences and facts about this particular approach. All these spin Hall effects are closely related to the Berry phase. Position operators become non-commutative. Let's not go into this at all. I don't want to go into this at all. Just let's ignore it.
By the way, the positions of electrons in the solid state, in the regime where the quantum Hall electrons also do not compute. So we cannot forget about it.
Yes. Okay, and last point to mention here, there is a similar effect predicted for gravitational waves. And this might be interesting because gravitational waves have very low wavelengths, very low frequencies as compared to photons. So maybe it would be interesting to look for the effect in that particular scenario. Okay, so now we come to the second approach, which is based on the Mathison-Papapetrou-Dixon equations. So we have here the Mathison-Papapetrou-Dixon equations, which are like the standard starting point for studying the motion of massive spinning particles in general relativity. But however, in our case, when you think about light, we have two problems here with the MPD equations. The first problem is that the system over here is underdetermined, so we need some supplementary condition in order to be able to solve the system. And the second problem is that these equations were designed for massive particles and not massless particles. So one would have to take somehow the limit to go to massless particles. Okay, and this has been done by Souriau and Saturnini in the 70s, I think, where they imposed a supplementary condition in order to close the system. This is the SP condition. It's widely used in general relativity, even for the massive case. And then, in order to describe photons, they impose this additional condition: p squared equals 0, and the spin tensor must be related to the helicity of the photon. And based on this extra condition, they arrive at some modified set of equations, which are called the Souriau-Saturnini equations and are meant to describe massless spinning particles propagating in GR. Okay, and now we can look at the paper by Duval, where he talks about these equations and he tries to put them to use. So in that case, Duval considers a Robertson-Walker metric like this, and then tries to integrate the equations and see how the trajectories look. Okay, he chooses some initial conditions, and then he does some numerics calculations and gets these types of trajectories. So here the orange line will represent an ordinary null geodesic. And then the blue line is what he gets from the numerics when he considers a photon with helicity plus or minus h bar.
Did he also discuss the relation of this picture to Maxwell equations?
No.
So how do we trust something which can...
No, I don't trust it. This is the point. I don't trust it. Yes, yes. Okay. So people over here get crazy stuff. So, for example, if you take things for granted, that you have like a point particle, and you see this helical trajectory, you immediately come to the conclusion that this is superluminal motion. But this is completely crazy, because
Why does dissipate along the line?
it's because of the time dependence that you have in the Robertson-Walker metric. You see, you have this expansion basically.
It's already an extremely large time limit, which means
Yes.
you can't use top metric anymore. So this
Yeah.
is going to contradict an assumption.
Okay, so as I was saying, the first thing that you see over here is that it looks like it breaks causality. But this is not the case. I mean, for example, if you take Maxwell's equation, then for Maxwell's equation you cannot have, I mean, you usually do not have initial conditions localized on a Dirac-supported region. You have initial conditions supported on a finitely extended region, not like over here where is a Dirac-like region. So, for example, if you have your initial condition, your beam, supported in a finite region, and then you look at the causal development of this region, then you do not have any problems with causality. So, for example, let's say the center of energy of your beam can do whatever it wants as long as it doesn't leave the causal development of the initial condition region. Okay, so this is very hard to compare with Schwarzschild because the two cases are widely different. And if we think in terms of angular momentum of light, there is no extrinsic orbital angular momentum in this Robertson-Walker metric. So the only possibility might be to interpret this as spin to orbital angular momentum conversion. This is just a guess. Okay. And I mentioned causality, so this is basically it with this approach. Okay. But there are some interesting connections. So, for example, if we forget the massless limit of the MPD and look at the massive MPD equations, there have been different proposals. First by Rüdiger, where he proposes that using the WKB approximation on the Dirac equation, one could recover the linearized MPD equation. And the same was proposed later on by Obukov, using again this Foley-Waltheisen transformation. So the question would be, can we extend this for massless particles? And the second question would be, can we go beyond the linearized MPD? For example, if we consider next order geometric optics correction, can we derive such an equivalence for the full MPD equation, not the linearized MPD equations? And these are things that we are currently thinking of and trying to work on. Okay, how much time do you have?
Almost 15 minutes.
15? Yes. Ah, okay. Okay. So the final approach is, I would say, the most standard from a GR point of view. It's the geometric optics approach for Maxwell's equation in curved spacetime. So by means of geometric optics approach, we arrive at the description of the propagation of light in terms of null geodesics in general relativity. And the main assumption is that the wavelength is much smaller than any other characteristic length scale of the problem. And we do this by considering the iconal ansatz, where we split, let's say, the vector potential into a slowly varying amplitude and a rapidly oscillating phase factor like this. Okay? And now we take the iconal ansatz and we plug it into the Lorentz gauge condition and into the wave equation, and then we identify order by order in omega. Okay, and then we arrive at this.
You need the potential, you have Maxwell equations that do not have the potential. potential. Then you don't have problems with the potential that you encounter.
Yeah, you can also do the expansion in terms of the F tensor. So you can also do it that way.
But then you don't have problems with, for example, gauge conditions.
Yes, exactly, exactly.
It does not make sense in this form. Why go through the
This is
method?
covariant derivative, right?
Yes.
A mu K mu is not a covariant derivative.
A,
Oh yeah, this is the problem.
this one.
Yeah,
This is just a contraction.
yeah, I know. So this gauge condition has no direct correspondence to the previous one where you use the covariant derivative on the
Alright.
previous transparency.
I'm not sure I understand what you're trying to say.
No, here,
Yes.
25.
Yes.
Is this the covariant derivative?
Yes, yes.
So it is not K, it is not a multiplication by K, if it is a covariant
This
derivative.
covariant derivative has a normal derivative plus some
Yes.
others, right?
Yes.
So it's a K plus something
Yes.
to make things.
Depending on gravitational background.
So if you look at this order, this is what you get at this order.
Order omega.
Yes.
The something is.
So this is standard textbook. If you pick any standard GR textbook, you can find these equations. Okay,
I
so
think it was Isaacson who first did that. Am I right?
I don't know.
Anyway, there's a paper by Isaacson who does it for whatever spin fields.
Mhm.
Also for Maxwell.
Okay, so the point is you can do it in different ways. You don't need to start with A. You can start with F, for example. And then exactly as you said, you don't need to worry about the gauge condition. But nevertheless, you should get this set of equations. Okay, so the first equation just tells us that these light beams will follow null geodesics, and the second the second and the third equation are transport equations. And in order to make sense of them, we must split the amplitude in the following way. We split the amplitude into a real part and a complex polarization unit vector. And then when we plug this back into the previous transport equations, we get the following two equations. The first one can be interpreted as the conservation of photon number along the null geodesic. And the second one is the parallel transport of the polarization vector along the null geodesic.
But in this equation, K mu is a function of space-time, right?
Yes. So K mu, it was defined over here.
So it's not the same, it's not a fixed vector, it is
No, no, no.
a function of space-time.
Yes, yes, exactly.
It's space dependent.
Yes. Okay, and now the next step is to introduce circular polarization based vector fields. These are E1 and E2 over here, and this will be a set of space-like vectors that are parallelly transported along the null geodesic. And then we can write L in this way, and we plug this in back into the parallel transport equation of L. And then what we get this equation which describes the behavior of this extra phase factor over here. And this phase factor gives us what is called the gravitational Faraday rotation. Okay, and now by different authors, it has been suggested that since we get this extra phase over here as the gravitational Faraday rotation, we might as well include this phase in our initial ansatz. So we include it in the initial iconal ansatz so that it gets modified in this way. And then using this modified iconal ansatz, they do the same geometric optics procedure as presented over here. And then instead of null geodesics, they get this modified null geodesics, where sigma over here is related to the polarization of the beam. And this, let's say this force term F mu nu, in Kerr, for example, is proportional to A. So you immediately see that here you get an effect in Kerr, but in contrast to the previous approach, you get no effect in Schwarzschild. And this is the first major contradiction that for me personally served as a main motivation for studying this effect. Okay. You can also write this as, equation 39 here as some effective metric in Kerr, for example. So this is the original Kerr metric, and you can write in this effective corrections over here to the Kerr metric and arrive at the same equation. again, these are proportional to sigma and go like 1 over frequency, so the effect goes away in the limit of high frequency. And here F1 and F2 are 0 if we set the spin parameter of kerr A equal to 0. Okay, so as I mentioned, here we have an effect in kerr but not in Schwarzschild. It goes away in the limit of high frequency. Okay, but what about the types of spin-orbit interaction that this effect captures? My guess here is that it captures only a particular coupling between the spin angular momentum of light and the spin of the Kerr black hole.
High frequency, you mean small wavelength, right?
Yes.
Yes.
Yes. Yes. Did I say it the other way? So it could be.
This is just the basic Eichel approximation.
It's iconal approximation, but you take in the next order corrections in the iconal expansion.
The small parameter is the wavelength to the
Yes.
characteristic size.
Yes. Yes.
of blade.
Exactly. Exactly. Okay, and a similar approach has been developed for gravitational waves. Okay, but clearly there is a problem. So because one approach gives us an effect in Schwarzschild, and this approach gives us no effect in Schwarzschild. So this.
This one approach is just wrong.
Yes, this one is wrong.
You don't understand their exact solutions of Maxwell equations in Kerr metric, Schwarzschild metric, which will give you the correct answer. Why go through all these approaches which are just wrong?
Can we talk about this afterwards? I'm really interested. I mean, I really want.
Appreciate the beauty of a Maxwell equation.
No, collect some points for categorization.
Okay, so since we have some disagreement between the first approach and this approach, one should start looking at ways to solve this disagreement. So one way to do this is to look back at how the spin Hall effect was originally derived in optics in homogeneous media, for example. And if you look at this paper by Blioch, which derives the spin Hall equations of motion, then you see that he has an extra phase factor in his iconal ansatz, which is the Berry phase. But again, this looks like an ad hoc modification, just like the previous one, where the gravitational Faraday rotation was again inserted into the iconal ansatz. This looks like an ad hoc modification of the iconal ansatz. And also, right now, I do not know how to compute this Berry phase in curved spacetime. This is another problem. So then I found out that there is yet another approach which seems to solve all the problems. I call it here Lagrangian geometric optics. So basically what the authors do over here, they take the geometric optics approximation at the level of the Lagrangian, and then in this approach they have a clear way of localizing wave into point particles. This is just a limit, an approximation in which waves are localized into point particles.
The Lagrangian for what system?
For whatever wave system. For Maxwell, for example, or for gravitational waves, or for it's quite general.
So for Maxwell equations?
Yes.
The full Lagrangian?
Yes.
Okay.
Yes. So they plug in the iconal ansatz into the Lagrangian of the Maxwell equation.
How do you make geometrical optics approximation on the full Lagrangian of Maxwell equations?
In the same way as above. You just take the A equals amplitude times phase, and you plug it in this Lagrangian, for example. I mean, I'm skipping a lot of steps here, but we can talk in detail about this. I can show you in detail this. I'm just trying to show you like the key points over here. I'm trying to present this approach in 2 slides, so I'm running out of time. Okay, so it's important that there is a clear way of localizing waves into particles in this way. And at the end of the day, after doing this localization, from a wave Lagrangian, we get a point particle Lagrangian. And it seems that the Berry phase contributions are included in this approach. Okay, so in a nutshell, we start with an action which, for convenience, here I put it in this Dirac-like form. It doesn't have to be in this form, it's just for convenience over here, I put it in this Dirac-like form. And then I take this type of iconal ansatz with an amplitude, a complex polarization unit vector, and the phase factor, and plug it into the Lagrangian. Okay, so in equation 50, I go from the full wave Lagrangian to an approximate wave Lagrangian, which looks like this. And because I have this overall A square factor, we can regard this as the intensity of the field. And due to this, we have a clear way of localizing waves into point particles by taking this limit over here, by considering the intensity of the wave as a Dirac delta function. And then if we plug this Dirac delta function here, we go from a wave Lagrangian to a point particle Lagrangian. So,
and what is the form of this Lagrangian?
I can show you. I don't have it here. I can show you the form and the equations of motion as well.
Because that's, I understand, the crucial result that you have, that you replace the waves by Lagrangian of a point particle.
Yes. So, for example, you get the same equations of motion out of this Lagrangian as the spin-Hall equation of motion in inhomogeneous media, if that's what you're looking at. And we have, right now, we're working on, and we have a method of extending this to arbitrary curved spacetimes. I can show you more about that afterwards, if that's interesting.
Z here, Z polarization.
Z is the polarization. It's a unit vector, complex unit vector. Okay. So let me come to the conclusions and open questions. So I think that the most important question that should be addressed is, can we experimentally test any of these predictions in any way? Can we measure this spin-Hall effect with satellites around the Earth, with a satellite at the other side of the sun? Or can we at least measure the Berry phase? And there are some strong experimental proposals for measuring this gravitational Berry phase. Okay, the second question would be, what is the best theoretical framework for addressing this gravitational spin-Hall effect? For those of you interested, we can talk afterwards. I'm currently working with some collaborators on a method for solving this problem. And another question would be, how does this affect black hole shadows? So someone asked me moments ago about the gravitational lensing. So that's like the far field regime of light bending. But in the strong regime of light bending, we look at black hole shadows. So it is expected that this spin-Hall effect should have a significant contribution in this regime when we look at black hole shadows. Okay, and another important question is, what are the implications for gravitational wave physics? The important point here is that the spin-Hall effect goes like 1 over frequency, and we know that the frequency of gravitational waves is in the order of 100 hertz, for example. So that's much lower than the frequency of light. So maybe the effect would be more significant in this situation. And then, okay, there are the crazy questions regarding the non-commutativity of position operators in curved spacetime. I don't want to go into the details over here. I mean, I don't know too much about it. It's just like a crazy question. And the last crazy question, which is obvious to ask given the results from condensed matter physics, is there a gravitational quantum spin-Hall effect? Not in the sense of quantum gravity, in the sense of having like a very strong gravitational field that gives some topological quantum effects as in condensed matter physics. Okay, thank you very much for your attention.
Okay, do we have any questions?
Yes.
So in the end, the most interesting result, if I understand correctly, is exactly this Lagrangian.
Mm-hmm.
You didn't show it, but does it look anything like a can you see any similarity to, let's say, the Lagrangian you get simply for null geodesic?
So if you look at the zeroth order geometric optics, you get explicitly that Lagrangian. And then if you look at the next order, you get the correction term, which is related to the polarization degree of freedom.
And this is a first order effect?
First order effect, exactly.
And this, what does this Lagrangian look like? Is it okay? Is it just a linear correction to the?
I can't put it in simple terms.
Okay.
But
well,
for example, if you, it will give you some polarization rotation, if you look in the linear polarization basis. And this polarization rotation could be related to, you can view it as a consequence of integrating over the spin connection along the path of the particle.
I see.
That's the intuition I have so far.
Okay, thank you. Anyone else?
I think, well, I would be careful with making a quick analogy between wave propagation, light propagation and gravitational waves. Of course, they have this, the same number that you characterize them with, which is frequency, but gravitational waves have intrinsically different polarization. You cannot have circularly polarized gravitational waves, right? So the polarization is different here,
Yes,
and probably you would have to have formally full development of the formalism for pure gravitational wave mechanics to see how this effect would cope with the frequency. I think the scanning may be not the same, like for light.
So as I mentioned, some of the approaches have this extension towards gravitational waves, and the only difference is that instead of having helicity ±1, you have helicity ±2. That's the only difference that they
Well,
get.
that's the simplest approach, but I think it's more than that. But anyway,
Yeah,
I think it was very
this
interesting.
remains to be analyzed.
A very interesting effect, and you should think about putting a ESA proposal maybe for putting some mirrors. It would be great to observe something like that.
And Professor Deo.
I have not understood really the main issue here. We do have here a theory which we know is correct. This is the theory we talk about classical wave propagation in background metric.
Yes.
Now, you presented many different approaches.
Yes.
Why go through all these approaches if we know what is the real theory? And the only way to do it is either to do it exactly or to do the approximation, but not the approximation to something that is not well defined, but the approximation to Maxwell plus background metric. And if one cannot prove that this is a good approximation, then there is no point of going through all these pains of introducing classical mechanics, because the approximation in all these other approaches is not controlled. To control the approximation, we must have a well-defined small parameter, which is the wavelength to the scale.
Yes.
This small parameter is really very small, and I do not know why bother, why go through these approaches that do not make contact with the real theory.
So you're suggesting that like the iconal approximation would be the...
I would not call it iconal, because iconal certainly in the standard sense misses the problem of polarization. Therefore, it should be an approximation to Maxwell equations that will take into account the vectorial character of electromagnetic field.
Exactly.
And this is a well-defined program, and this is the only one that we know makes sense. All these approaches, when one gets classical equations from somewhere, do not really make physical sense.
I totally agree, and this is what we're working on right now. Using this last approach that I mentioned, this is what we're...
Why don't you forget about the part of your talk which you devoted to something which does not make sense?
I will forget about it as soon as I have the result for this last calculation that we're doing. And one point here, so for example, there are these Fourier-Saturnini equations which come from MPD equations. Massless, if you take the massless limit of the MPD, you get this Fourier-Saturnini. So if you can prove that using geometric optics in the standard way with these added corrections coming from polarization, you get the same equations of motion as this Fourier-Saturnini equations of motions, then these Fourier-Saturnini equations of motions can be useful. Otherwise, they're just, you can throw them away. This is... I agree.
Okay, do we have more comments? Jarek?
Related to what Professor Białowski-Blula was asking. So why nobody has just simply took and numerically integrated Maxwell equations on the, say, Schwarzschild or Kerr metric, or is it still too difficult?
I try to convince a lot of people to do this, but
Like really, I mean, we have the most basic theory, which is Maxwell equation on the curved background. Then you try. I mean, we have fantastic computers. You first, to get some intuition, you try to integrate them numerically.
yes, I agree.
And hopefully, well, pray or whatever that you see some effects, and then you try to see if you can reach it with a proper theory. Or nobody has done it as far as I
nobody
understand,
has done it. I agree that this should be like a proof of concept that this effect holds.
And do you know why nobody has done it? Is it like numerically
I
too
think it's very difficult.
or nobody had this idea?
I think it's just as difficult as using full Einstein equation to propagate gravitational waves.
No, it's not that bad.
It's not.
These are Maxwell equations are linear.
It's not that the equations are linear or non-linear. That doesn't seem to affect the computations too much. It's not that it's just that it's a four-dimensional problem, so you need a really huge grid, and the wavelength of the wavelength is really small.
The computers are now huge as well.
Definitely.
They start to gravitate because they are so big, so this distorts their calculation.
Definitely making such numerical calculations, you would like to have some independent insight just to visualize or to imagine what kind of answer you may expect. But there are exact solutions, yeah. And also, your last fundamental question, whether there is this polarization Hall effect in gravitational field, in a sense must be, because if you propagate through the vacuum, there is no vector you can couple polarization to, because vacuum does not provide you. But if you have any inhomogeneity, then of course this inhomogeneity by definition defines directions, etc., etc. There are thousands of possibilities what can couple to, and what couples, in fact, if you solve this equation numerically or exactly, to electromagnetic vector field, right? The question is how to pinpoint its general properties, the most important properties. I mean, to make a conclusion without having to solve the propagation through the whole universe or something like that.
Okay, so I guess we don't have any more questions and comments, so let's thank Marius once again.